Welcome to EDU World Space.
Okay, from the model that has been described to us from the problem, we can simplify it to a mass right here attached to a motor with a spring. And the only two equations that we're going to be using is the amplitude of vibration equation and the harmonic frequency equation, right, as seen over here. And the conditions as given to us is that xm, the amplitude of vibration, will be exceeding 3 times the static deflection as seen over here, which is in uh, delta. Okay, so we pretty much have to find the bounds of omega frequency as our end goal. First, we could just plug in 3 times omega m into the amplitude of vibration equation. So it's going to look like as so, 3 times the omega m. We're just at the bounds of the omega m right now. I mean xm. And we could just equate this thing, since xm is equal to 3 delta m, and equate to the equation 1 minus omega f over omega n over, squared. Okay, now we just focus on this equation over here. The delta m cancels out, and we are left with 3 equal to 1 minus omega f over omega n squared equals, uh, putting the denominator on the left hand side, we would have this, and the 3 on the right hand side. And let's simplify even further. We are left with omega n squared equals 1 minus 1/3. 1 minus 1/3 is 2/3. And we'll just simplify this further. I'm just putting the square root here to remove the squared, plus or minus. But since we know that angular frequencies would be positive, we'll keep the positive. 2/3. There we go. And since we know the harmonic frequency, it's going to be k over m. Finally, we will have 2/3 k over m square root. Now, this will only be the lower bound of the forced circular frequency. How would we find the other one? Well, let's look at the xm. Xm would be 3 times of the delta m, the static deflection, but we're only focusing on the positive side. Let's not ignore the negative side, because the motor itself, as seen in the model itself, as seen in the model, it could actually rotate to the other side. So this would be negative m, since it's rotating. So it's not only that xm exceeds 3 times delta m, it's also going to exceed 3 times delta m negative. And this derivation is very similar to what we did just now, and it's right down here. But as you can see, it's going to be equate to -3 delta m. And lo and behold, we would have our bounds for the forced circular frequency. So putting it all together, we would have this. Omega frequency is less than 2/3 of k over m square root. And, oh, whoops. It's going to be 4 on this side. And this would be our range for forced circular frequency.